Today we're going to talk about networks and internet architecture and why they are the foundation of modern computing. Without networks, there would be no cloud. This is really the invisible backbone that makes our apps and services possible. Networks and internet architecture. When we think about cloud computing, I hope we still don't imagine the cloud as an actual cloud, but servers humming in a giant warehouse somewhere far away. But those servers would be useless if we couldn't reach them. And this is where networking comes in. The story of cloud is really the story of internet. As the internet grew faster and more reliable, the cloud grew alongside it. In 1990s, when people were still dialing up modems, the idea of streaming Netflix from cloud would have been impossible. You'd wait for an hour just for the homepage to load. But with broadband in 2000, suddenly YouTube and Gmail began flourishing. And now, with fiber, 5G, and undersea cables connecting the continents, massive platforms like AWS and Azure can deliver cloud services instantly anywhere in the world. Why networking matters? Networking is what makes cloud useful. Without networks, everything is unreachable. Every time you open Instagram, send message on WhatsApp, or back up your photos on iCloud, you're relying on the network to connect to your device to a server somewhere else. The better the network, the smoother the cloud experience. That's why internet speeds and reliability directly shape what cloud services can do. Technically, a company doesn't always need public internet like cloud. They can build their own private cloud like a LAN, which stands for Local Area Network. This is like having a private highway that only employees can use and reach the servers inside the company. It's faster, safer, and totally under their control. But here's the thing, private LANs are limited. They're great for internal projects or communications, but once you step outside, you can't connect. Now the question is, who gives us these networks? The answer is internet service providers or the ISPs. These are the companies which we pay every month for Wi-Fi or mobile data, like AT&T, Verizon, T-Mobile, Spectrum, all of those companies. They are the ones that lay down the cables, run the routers, and keep the internet highways open. The internet is made up of many ISPs connected together. No single company owns the whole thing. Each ISP controls its own piece and connects with other at giant switching points. This is why the internet is decentralized. If one provider has issues, traffic can reroute through another. Figure shows that how ISPs connect with each other and with the organizations. Governance and ICANN. You might be wondering, if no one owns the internet, then who's in charge? The truth is, nobody runs the whole thing, but there are groups that help coordinate it. One important one is called ICANN, which stands for Internet Corporation for Assigned Names and Numbers. They make sure when you type google.com, your browser always goes to Google servers, not somebody else pretending to be Google. ICANN is like the phone book manager of the internet. They don't run roads, but they make sure that the names match with the right addresses. Now, government also steps in. They enforce national regulations, like things like privacy laws, censorship rules, or data security requirements. For example, Europe has GDPR, which has strict rules about how companies can use personal data of its users. China has its own national firewalls, and also the US has its own internet policies. But here's the fascinating part, even when all these local rules, the internet as a whole remains globally decentralized. No single country or company controls everything. Instead, it works because these different networks agree to connect and share traffic. That's what makes the internet both powerful and sometimes a little messy. Internet topology. Let's picture how internet is structured. Think of it like a three-tier design. At the top are the tier 1 providers. These are global giants that own the backbone of the internet, including the undersea fiber optic cables that cross the oceans. They make the worldwide communication possible. Below them are tier 2 providers. They cover large regions like entire countries or states. They connect to the big tier 1 networks but also run their own large scale infrastructure. Finally, at the bottom, they are tier 3 providers. These are the local companies you pay every month. They don't connect with the whole world, but they connect your home or your phone to the bigger internet. Figure shows this hierarchy clearly. And remember, as this topology has grown more advanced, the cloud has been able to grow with it. Without fast tier 1 providers, global cloud services would never work. Internetworking components. Now let's talk about the actual mechanics of how data moves around. There are two core ideas here. First is packet switching, breaking the data into small pieces, and second one is router, the device that forward these pieces and assemble them. Connectionless packet switching. Let's imagine you want to mail a 500-page book. You can't send all at once in one envelope. It would be too big. So instead you break it into smaller pieces and send them separately. That's what the internet does. It divides everything into smaller packets, which are like the envelopes, and each packet has a label with the destination address. That is the IP address. They don't all travel in the same way. Some packets may go through New York, others through Chicago, but at the end of the day, they arrive and get reassembled into the original message. Routers. Now, who does all of this sorting and forwarding? That's the job of the router. It looks at each packet and reads the addresses and decides which road to send it down, or even if the packets belong to the same video file or a text document, the routers treat them one by one. Some may take one route and some other. They choose the best next hop dynamically. The important part is that all eventually get to the right place. The figure shows how a router takes in the packets and forwards them so they can be reassembled into the original message. Path redundancy. This design means the internet has built in redundancy. If one path is blocked, packets can take another route. That's why even if a cable under the oceans get cut, the internet still works. Data just reroutes automatically, but there's a trade off. Sometimes rerouting takes longer, and that delay is what we call latency. That's why Zoom calls sometimes freeze or lag. That means your packet are taking a detour. Physical networks. Underneath all of this logic, there are physical networks that are actual wires, like fiber optic cables and radio signals that carry the data. They work in two layers. The first is the data link layer, which makes sure that the packets move between neighboring nodes without colliding. The second is the physical layer, which is the real medium. Even though we call it the cloud, the truth is your data always ends up traveling through something physical. Transport layer protocols. On top of the physical layer, we have the transport layer protocols. The two big ones are TCP and UDP. TCP stands for Transmission Control Protocol, which is reliable and it makes sure every packet arrives in order. It's like a certified mail where the sender gets a receipt, but it's a bit slower because all of the checking that happens inside. UDP, which stands for User Datagram Protocol, is faster but it's less reliable. It is like dropping flyers. Most get delivered, but you can't guarantee everyone gets delivered or not. Different applications choose different ones. For example, banking apps use TCP because they need accuracy and that's all it matters. But live streaming and games often use UDP because speed matters more than for perfection over here. Application layer protocols. On top of TCP UDP, we have application protocols. These are the ones you actually recognize. HTTP and HTTPS are for websites. SMTP is for email. BitTorrent is for peer to peer file sharing. SIP is for internet telephony. Now, what does telephony means? It's just a fancy word for voice calling, basically a telephone service. Traditionally, telephony is what your grandparents used when they picked up a landline phone. Internet telephony is sometimes called as VoIP these days. VoIP stands for Voice over IP, which means making calls over the internet instead of using old telephone line. Apps like Skype, Zoom, and even WhatsApp calls are examples of internet telephony. SIP, which stands for Session Initiation Protocol, is the system that sets up and manages those calls. Who's calling who, when the call starts and when it ends. Whenever you use internet calling, you're actually using internet telephony powered by protocols like SIP. Every app you use is built on top of one of these protocols. They are like the languages apps use to talk to each other across the internet. Protocol stack. This whole structure is often shown as a layered model called the Internet Reference Model or the TCP/IP stack. This figure shows it clearly. At the bottom is the physical layer, which is the wires and signals. Above that is the internet layer, which handles IP addresses and routing. Above that is the transport layer with TCP and UDP. And at the top is the application layer with protocols like HTTP. This design makes the internet flexible. You can upgrade one layer, like adding faster fiber optic cables, without breaking the others. That's why the internet has been able to evolve smoothly for decades. On premise networking. Before cloud computing, companies usually built their own data centers. They kept servers in their own buildings managed by their IT staff. Employees would connect through the company's private LAN. This gave companies a lot of control over the security, but it was expensive. And guess what? This is basically the idea behind private cloud. Let's break down this picture that we have in front of us. On the left, inside this big cloud shape, you see a group of servers and computers. That's the private cloud network, basically the company's own data center. Everything here is owned and controlled by the organization. Employees sitting on those desktops connect directly through the server over the local network, which is the company's internal wiring. Now, notice the blue router at the edge. That's like the front door of the private cloud. Before the traffic goes out to the world, it passes through this router and then through the firewall. The firewall is the vertical bar in the middle, and the firewall acts as a security guard checking what traffic is allowed in or out. Once traffic is cleared, it heads through the corporate internet connection shown here with the globe and the red routers. This is the company's link to the outside world. Employees working remotely, maybe at home or on their phones, can still reach their corporate servers. On the right side, the diagram you see are the users, a person on a laptop and a person on the phone. They are not inside the company building, but thanks to the internet connection, they can still access the same cloud services remotely. So, in terms, this diagram shows how a private cloud works. Everything is hosted inside the organization, but it can still be reached from outside through the internet as long as you go through the firewall and the corporate connection. This gives the company both control and flexibility. Internet based cloud. Today's most companies don't want to run all of their servers. Again, basically the idea behind the public cloud. Okay, now let's compare this diagram to the private clouds diagram. Here, instead of everything being inside the company, you see two separate parts, the cloud consumer network at the top and the cloud provider network at the bottom. On the top left, the consumer network looks similar to what we saw before. Servers, desktop, router, and a firewall. This is the company's own internal network. Employees sitting inside the building can still access it, but here's the big difference. The green line shows a direct path from the company's network through the corporate internet connection all the way through the cloud provider's network at the bottom. That big cluster of boxes represent the provider's massive data centers, racks and racks of servers at Amazon, Microsoft, or Google. On the right hand side, you notice remote users again. They can connect through the internet, not just through the company's internal systems, but also directly through providers' cloud services. So even if the employee is working from home using their phone, they can still access the same apps hosted by the provider. In short, this diagram shows how the internet becomes the bridge. Instead of keeping everything locked inside a private LAN, organizations rely on providers' global infrastructure. The provider manages the heavy lifting, and the consumers connect over the public internet. So this is how public cloud networks works in practice. The company connects its users' devices to their external cloud services while the provider runs the giant server farms in the background. Let's look at more on-prem versus cloud access and revisit all of this topic in the next class. I still didn't get the Zoom access, so I'll try to record the session which we were planning to do for live until I get the Zoom access. I'll try to record it over the weekend and I'll post it along with the Monday's class. And thank you.